All right, so good morning. We're gonna continue with momentum, and understanding momentum fully is very important. So again, when we talk about momentum, we're talking about mass and velocity. A moving object is gonna have a momentum, and when we consider collisions, it's an inter. When we define collision, it's an interaction between two objects that made contact with each other. Um, and of course, when objects collide, force is being applied between the two colliding objects. So when objects collide, they come in contact with each other, and they're sort of transferring force. Okay, one object is gonna apply a force on the second object, and then the second object is gonna apply a force on the first object. Okay, remember that from Newton's third law, force comes in pairs. So if one object apply a force on another object, the other object is going to apply a force also on the first object, and it's going to be equal in terms of magnitude, opposite in terms of direction. Okay, so try and get that concept. Okay, so there are different types of collisions, and we will come back to this, the different type of collisions. So don't get bogged down in it just yet, but further on in the lecture series, go over what is inelastic collision and what is elastic collisions. When we talk about an elastic collision, because there are different types of collisions, when we talk about elastic collision, the objects rebound usually with the same speed as they had prior to the collision. So take for instance, if you throw a ball and the ball hit the wall, sometimes the speed with which the ball strikes the wall, when the ball rebounds, sometimes it have the same speed as it was going towards the wall. It rebounds the same speed. That would be an example of what we call elastic collision. So, so again, objects rebound with the same speed as they had prior to the collision. So you'd say that the momentum, which is mass times velocity before the collision, is almost the same as the momentum after the collision of the ball with the wall. Okay? So when you talk about elastic collision, we usually have large velocity change. We usually have large momentum change, because remember, momentum is mass times velocity. So if you're going to have a large velocity change, you're going to have a large momentum change. And remember that momentum change is the same thing as impulse. Force times time is equal to the impulse, and the impulse is equal to the momentum change. So we're talking about the elastic collision having large force. So just bear that in mind. We will go over this again. But if you remember, when we say impulse, impulse is the force that is involved in a collision, and the time that the time that the collision occurs. Okay, so and we derived this at first. Okay, we did a derivation of this. So just imagine if you strike a wall, if you hit a wall with your fist, you're going to use a certain amount of force, and you're going to hit the wall for a certain amount of time. So the force that you apply in striking the wall, and the time of the contact between your fist and the wall, that force times the time is what we call the impulse. And again, impulse is the same thing as momentum change. And we call this the impulse momentum change theorem. So if if you're talking about a scenario, when you look at a scenario, they a lot of time the impulse is fixed. What we mean by that is that the force times the time that the force is being applied is usually a relatively fixed number. Okay, so we have to get that concept. The force that you're applying times the time that the force is applied. That force times time is called impulse. And the impulse is the same thing as momentum change, and we call that the impulse momentum change theorem. So if the impulse is a fixed quantity, then you can see that the force and time are inversely proportional to the impulse. Because if I impulse is a fixed number, okay, then if you increase force, you're going to increase impulse. If you increase time, you increase impulse. But if this is a fixed quantity, then the force and time is going to be inversely related to each other. So that is because if I is a fixed quantity, then if time increase, force have to decrease. If force increase, time have to decrease. And it's very important to note that the relationship between force and time are inversely related. So if you increase one, you have to increase the other. What we mean by that, when you have collision, the collision time is a very important one. Because since usually in a collision, the impulse is a fixed number. If you can increase the time of collision, then you can decrease the force of the collision. So the greater the time, the smaller the force of the collision. Think about it. The greater the time, because we say that impulse in a scenario is a fixed number. So if you increase the time, you can reduce the force of the collision. So decrease the force on an object in a collision, the time must be increased. And we use this in practical situations because if you're going to collide, say you're going to collide with the wall, you're going to collide with a wall. You want to try and reduce the force of your collision as much as possible. Because if you can reduce your force of contact with the wall, you can reduce injury. Think about it. You can reduce injury if you can increase the time of collision, because you're going to decrease the force, right? Remember, impulse is usually a fixed number. So if you can increase the time of contact or collision, you can reduce the force. Force is what's going to cause injury. All right? All right, let's move on. So in practical scenarios, we use airbags. When you're driving, when we use airbags in collision for a reason. Because, all right, if you're driving a car without an airbag, and you are involved in a collision, God forbid, you're involved in a collision. Remember, the impulse is usually a fixed number. The impulse for that collision is going to be a fixed number. Impulse is equal to the force times the time. The force of the contact that you're going to make, and the contact you're going to make is with the steering wheel or the dashboard. Okay? And what's going to happen? You're going to your chest is going to be exerting a certain amount of force on the steering wheel or the dashboard over a certain amount of time. And that force times time is what we call the impulse. Again, you can reduce the force by increasing the time. Because for that scenario where you're going to hit the steering wheel or the dashboard, that impulse is usually a fixed number. It is equal to the force that you're going to apply times the time of the contact you're going to have with the steering wheel or the dashboard. So if you can increase the time of contact with whatever you're going to hit, then you can reduce the force. And using an airbag, you can do that. When you use a hairbag, so think about it now. When you use a hairbag, instead of having instead of striking a rigid surface or a rigid object, you're striking a hairbag, which is gonna have a little give. So when that little give is gonna increase the time of the contact, and by increasing the time of the contact, you're gonna reduce the amount of force that you're gonna strike the hairbag. So that is the rationale for using airbag. It decreases the force of the collision because it has that little give. Whereas the dashboard and the steering don't have that give. When you strike the dashboard or steering wheel, you're going to strike it for a very short time, very, very short time. But the force is going to be tremendous. This force is going to be very, very high because impulse is equal to force times time. Impulse in that scenario is going to be a fixed number. So if you decrease the time, the force is going to be a large number. Okay? So that is the rationale for a hairbag. Increasing the time of your collision, hence you're decreasing the force. Okay? Similarly, if you're in a gymnasium and you're jumping up and down, gymnasium tend to have a padding. Okay, there's tend to be padding around, and that padding, the reason for padding is to increase the time of contact or the time of collision. Because if you increase the time of contact or collision, you're going to reduce the force, the contact force or the collision force. Similarly, pole vault pits. When pole vaulters jump over and they drop on the pit, it's not a solid surface because you want to increase that contact time. You want to increase that contact time because force time time is a fixed number. So if you increase one, you can decrease the other. So pole vault pits tend to be, you have these padding which increase the time of contact. Similarly, baseball gloves. Someone catching baseball or who play cricket, the gloves tend to be padded as opposed to if you just use your hand alone, because your hand is not padded, that contact time is going to be short. Contact time short, huge force, and that's going to hurt. Again, goalie mitts, the boxer's gloves, the similar reasoning for boxer's gloves. Boxer gloves are padded to some extent because you want to increase the contact time, hence reduce the force. People would traumatize each other in boxing matches. That is the reason for using gloves. You increase the contact time, because if you increase the contact time, you're going to reduce the force. And similarly, for football players, they use these helmets that are padded. Okay, people who do rock climbing. Similarly, rock climbing. When you're doing rock climbing, you tend to use nylon ropes as opposed to rigid ropes, because if you use a rigid rope and you fall off the rock, the impulse, which is equal to force times time, you know, if you have a rigid rope, when you fall off, the contact time is going to be short. The force that you're going to apply on that rope is tremendous. So you will, because the force is so huge, you'll tend to let go of the rope and then fall, as opposed to if you have a nylon rope. When you fall off the rock, the rope is going to give a little bit, so your contact time with that nylon rope, it's going to stretch a little bit. It's going to increase the contact time, so the actual force that you're feeling is going to be reduced. So, for those of you who do bungee jumping, is the same thing. If you bungee jump with a stiff rope, 100% of the time you're gonna fall. You're gonna fall off because that contact time is so short. The force that you're gonna apply in that rope is tremendous, and you won't be able to hold on. Okay. Similarly, if you want to be cute, you can do what we call water balloon catching. And in order to catch a water balloon, so what you do, so you fill the balloon with water, and you fill the balloon with water, and you try to catch it. You can catch it if someone throws the water balloon to you, and when you catch it, you move back a little bit, and you increase the contact time, and you reduce the force that the balloon and water have. If you don't do that, if you just stand in place, the balloon is going to burst, because the impulse, which is the force times time, is going to be huge. Because if you're not going to move back, the contact time is going to be very small, very short contact time. The force is going to be huge, and that will break the balloon. Similarly, if you throwing eggs into a bed sheet, okay, if you loosen the sheet and the contact time is increased, those eggs will not break. As opposed, if the bed sheet was thick and the contact time was short, the force is going to be huge, and the eggs will break. So throwing an egg in a bed sheet is another experiment that you can do. Okay, contact time, collision time is very important. If you're falling, say you fall off a roof. If you fall off a roof, you want to try and get into a situation where your contact time with the flooring or the ground, if you can increase that contact time, then the force that you're gonna apply to your body is going to be reduced. And one way of doing that is bend your knees. So if you fall, and you must have observed this in everyday life. If you're jumping from somewhere, if you bend your knees and you sort of lower yourself a little bit, increasing the contact time will reduce the force of collision, or the contact force, and it won't be, you probably won't break any bones or feel any tremendous pain. So increasing collision time will reduce the force. Okay. So similarly, so you're jumping up and down. If you bend your knees, you will increase the contact time, and reducing the force. Okay. Remember, impulse is force times time. If you increase the time, you decrease the force. If you decrease the time, you're going to increase the force. Right? Um, Again, when you're driving, and if you meet in an accident, just strike a wall. Um, if you strike a wall and you bounce off the wall, if you bounce off a wall, then the momentum change tends to be a large one. And again, momentum change is the same thing as impulse. So if the momentum change is large, the impulse is going to be large. Hence, you tend to have larger forces. But you can decrease the force by increasing the collision time. So another practical scenario is the design of cars. What they're doing today, the manufacturers are actually designing cars so that when cars collide, either car to car collision or car to an object, a wall, a tree, whatever, cars are now designed to crumple up. Okay, of course, you're going to have the protective cage in which you sit and you drive, that's going to be protected. But the cars are now designed to crumple up so that you can increase the collision time and reduce the force of the collision. The older cars were rigid. The older cars were rigid. So when you hit something, it's going to be a very short contact time. The force usually is tremendous, and all sorts of damage usually occur. So cars are now being designed, when they collide with something, they crumple up, and the mere reason for that is to increase the collision time. So they're less likely to rebound because of decreased force. Simple, impulse is equal to force times time. So once you can increase that collision time, you can reduce the force. And there's a lot of practical implication for that. Okay, so of course, where the passengers are, there's a protective cage there, but the cars are going to crumple up and they tend to stick together because the force is going to be reduced, so they're not going to bounce off each other. Okay, that's a practical scenario there. So again, when we talk about collision of anything, Newton's third law is applicable. Because when two objects collide, they're going to exchange forces. The forces are going to be equal in magnitude but opposite in direction. So both objects experience forces that are equal in magnitude but opposite in direction. Just think about it a little bit. If you have two objects colliding, one object is going to slow down and the next object is going to speed up. Okay? So what we're saying is that one object will gain momentum because momentum is mass times velocity. So one object is going to lose momentum and the second object is going to gain momentum. You may say, well, suppose the two objects collide together and they stick together. Yeah, well, one object is going to gain momentum, the one that was moving slower or was at rest, and then the one that was speeding up and caused a collision, is gonna lose momentum. So when objects collide, one object will gain momentum and the other object will lose momentum. So if an object gains momentum, assuming that the mass is constant, then it's going to speed up. And then if the other object that slows down, assuming that the mass remains constant, it's going to slow down. Okay? So just a little bit of, conceptualize these things. When objects collide, one object is going to lose momentum and next object is going to gain momentum. Okay? So let's think about it in a more mathematical term. So when we say when object collide, One object will gain momentum, one object is going to lose momentum. So when we talk about force, a net force, remember, force is equal to mass times acceleration. So, you're going to have force being applied. It's going to be equal but opposite in with the objects. But force is equal to mass times acceleration. So once you have a net force being applied, you're going to have an acceleration. Okay, you're going to have an acceleration. Okay, uh, the objects, the mass tends, the mass of the objects in a collision usually remains the same unless it breaks up or stuff like that. Usually remains the same to a large extent. Um, so what's going to happen is you're going to have an acceleration. Okay, all right. So let's look at some examples. If you're playing golf and the interaction between the golf club and the ball. So when you swing the golf club, okay, that's going to have a certain amount of momentum. And when you hit the ball, okay, the the the, the golf club is going to lose momentum, and the ball is going to gain momentum. So just think about it. You know, Hitting a ball with a golf club, you're gonna the golf club is gonna hit the ball, so the golf club is gonna actually lose momentum, and the ball is gonna gain momentum. The 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 momentum that the golf club lose is gonna equal to the momentum that the ball gains. The reason why the ball moves so fast is because it has a smaller mass. The net force, because of Newton's third law, the net force, the force of contact between the golf club and the ball is going to be, the same. The golf club is going to exert a force on the ball, and the ball is going to exert a force on the golf club. But because the ball mass, remember, net force is equal to mass times acceleration, the mass of the ball is smaller than the golf club. Hence, the acceleration of the ball is going to be much larger than the golf club. Okay. Similarly, if you play pool, you know the interaction between the moving ball and the one at rest, same thing. The moving ball is gonna lose momentum, and the ball at rest is gonna gain momentum. So usually in collision, you're gonna have that. Okay. So again, when you strike the ball zooms away, and the golf club, slows down a bit. The ball speeds up, but the ball speeds up. The golf club slows down. Okay. The reason why the ball moves so fast, the net force on both of these things are the same. The net force on the ball is the same as the net force on the golf club. But because the ball has a smaller mass, it moves with a much greater acceleration. Remember, force is equal to mass times acceleration. So if you have a smaller mass, the acceleration is going to be greater. So we come now to what we call the law of momentum conservation. So what I've been saying so far is just the law of momentum conservation. And the law of momentum conservation states that in a collision between two objects in an isolated system, so we will discuss what an isolated system is. So in a collision between two objects in an isolated system, the total momentum before the collision is equal to the total momentum after the collision. So let's take, you can take any scenario. If you have a car that is parked and one that is moving, you take the momentum before the collision, it's going to equal to the momentum after the collision in an isolated system. Okay, so the total momentum before the collision is equal to the total momentum after the collision. One object is going to gain momentum and the next object is going to lose momentum. Remember, momentum is mass times velocity. One object is going to gain momentum and the other object is going to lose momentum. So for the law of momentum conservation, when you have a contact or collision between two objects, one object is going to exert a force on the second object, and the second object is going to exert a force on the first object. Okay, so the magnitude of the force is going to be the same, but the direction of the force is going to be opposite, and that is why we say FA is equal to minus FB if you have objects both A and B. So if you have objects both A and B, then the magnitude of the force is going to be the same, but the direction is going to be different. Remember that when you have a collision, impulse of that collision is the force times the time, and we know that force times time is which is the impulse, is equal to momentum change. So the impulse in one object is equal to the impulse in the second object. It's just that the impulse is going to be in opposite direction because the force is going to be in opposite direction. And again, impulse is equal to momentum change, which is the mass time velocity change. So the mass time velocity change, which is the momentum change in on one object, is equal to the momentum change on the second object. Okay, let's look at some scenario. So if you have a scenario where you have a firefighter fighting some type of fire, then if the firefighter has a hose and he is using the water to out the fire. So the hose gonna emit a large amount of water at a high speed. Okay? Why would such a task be difficult? So when fighting fires, a firefighter must use a great caution holding the hose that emits a large amount of water at high speed, because in that little isolated system, when the water is coming out at a high speed, the water is going to have a certain amount of mass, and because of the high speed, you're going to have a large amount of momentum, large momentum. So again, the force of the water going outward is going to force the hose backwards. Okay? So the momentum of the water going forward is going to be very high because of the high speed, mass time velocity. So the momentum going backwards is going to be very, very high as well. Okay? Again, if you're talking about impulse, which is force times time, so the firefighter has to hold the hose firmly because the tremendous momentum will be going backwards. It will push him back, okay? Because of the high speed at which the water is coming out. You're going to have a large momentum. The momentum is going to be conserved in that isolated system. So if the water is going to gain momentum, something has to lose momentum. Okay, so the hose, the firefighter is going to be pushed backwards. Okay, it's going to be a difficult task. All right, all right. So if let's look at another scenario. So a large truck and a Volkswagen have a head-on collision. Okay, large truck, Volkswagen, head-on collision. Which vehicle experienced the greatest force of impact? Again, so the 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 impulse, which is the force of contact times time, okay, is equal to momentum change. So which vehicle is going to experience the greatest force of impact? Collision between a large truck and a Volkswagen. Remember, the force is going to be the same magnitude. The force is going to be of the same magnitude, and the time of contact is going to be the same. So both vehicle is going to experience the same amount of force of impact. Okay? Which vehicle experienced the greatest impulse? Again, impulse is force times time. The two vehicles are going to collide or have contact for the same amount of time. So this force is going to be the same, but in opposite direction. The time is going to be the same. So the impulse is going to be the same. The impulse is going to be the same. Which vehicle experiences the greatest momentum change? Impulse, again, impulse is equal to momentum change. So both vehicles are going to experience the same momentum change. Which vehicle experiences the greatest acceleration or the greater acceleration? Remember now, the force is going to be the same. Net force is equal to mass times acceleration. Because the Volkswagen has a smaller mass, it's going to experience a greater acceleration. That is why it will speed up or it will be thrown because it has a smaller mass. The net force is equal to the same, but the net force is equal to mass times acceleration. So the smaller mass object is going to experience the greater acceleration. Okay. All right. So let's look at this case again. Miles Tugo and Ben Travelin are riding in a bus at highway speed on a nice summer day when an unlucky bug splatters on the windshield. Miles and Ben begin discussing the physics of the situation. Miles suggests that the momentum change of the bug is much greater than that of the bus. After all, argues Miles, there were no noticeable change in the speed of the bus compared to the obvious change in the speed of the bug. But Ben disagrees entirely, arguing that both bug and bus encounter the same force, same momentum change, and same impulse. Who do you agree with? Again, the same thing. Colliding force between two objects, the force experienced by the two objects are going to be the same, but in opposite direction. The time of the collision is going to be the same because they're going to come together for a specific amount of time. So the impulse is going to be the same. The momentum change is going to be the same. The only difference is going to be the acceleration. because force is equal to mass times acceleration. The smaller mass object is going to experience the greater acceleration change. So just simple physics. Okay? All right. So if a ball is projected upward from the ground, so you throw a ball upward with 10 units of momentum. You throw the ball upward, 10 units of momentum. What is the momentum of the recoil of the hurt? So, you throw something up, okay? So again, so it's going up, so the momentum is upwards, or the impulse is upward, okay? You're going to have a downward impulse as well. You're going to have a downward impulse, okay? The force with which you throw the ball upward is the same force that's going to push downwards, or the recoil force. So you're going to have a recoil force which is downwards. But the reason why you don't feel the hurt moving under your feet is because of the huge mass of the hurt. Again, the force is equal to mass times acceleration. So if you have a very, very huge mass, the acceleration is going to be negligible. So you're not going to feel this. Okay? All right. So let's look at this example. A 5-kilogram ball is projected upward at a velocity of 2 meters per second. So you throw a ball 5 kilograms upwards with a velocity of 2 meters per second. So what is the recoil velocity of the hurt? So the momentum of the ball is mass times acceleration. So the momentum of the ball is 5 times 2, which is 10, and that's upward. The recoil velocity of the hurt, same thing. So the velocity recoil of the hurt is the mass time velocity, because the two is going to be the same. Okay, the momentum. So the one object is going to gain momentum. So when you throw the ball upwards, the ball is going to gain momentum, and the hurt is going to lose momentum, or the hurt is going to go downwards. So the momentum of the ball is 5 times 2, which is 10. The recoil of the momentum change of the hurt is going to be the same, 10. The momentum change of the hurt is going to be the same, 10. Well, again, momentum change is equal to the mass time velocity, or momentum is equal to mass time velocity. So the mass of the hurt is 6 times 10 to the 24 kilograms. So you're going to multiply this mass times the velocity, and it's equal to 10. Okay? So let's just write this out. So again, momentum for the ball is equal to the mass of the ball times the velocity of the ball, times the velocity of the ball. And that is equal to, so the mass of the ball was 5 kilograms. So 5 times 2, which is the velocity. So that's equal to 10. So that is the momentum going upwards. So the momentum going downwards is the same. Okay? The momentum is conserved. Momentum going upwards is equal to the momentum going downwards. For the hurt, so we know that the mass of the hurt is 6 times 10 to the 24 kilograms. 6 times 10 to the 24 kilograms. That's the mass of the hurt. So if you multiply it by the velocity that the hurt is going to recoil, that's equal to 10. So that is equal to 10. So if you simplify that for the velocity, so the velocity of the hurt, or the recoil of the hurt, is equal to 10 divided by 6 times 10 to the, so it's 10 divided by 6 times 10 to the minus, sorry, 6 times 10 to the 24 power. Okay, so you can say 6 into 10 is 1 point whatever. So it's about for 6, so it's probably 1.6 or 1.7 times 10 to the minus 24. That is the velocity, minus 24, and that's meters per second. So you see the velocity is negligible, and that is why you don't feel the recoil velocity of the hurt, because it's negligible, because the momentum is conserved. Okay, so this is just an example of how we can use the conservation of momentum to work out scenario, because the momentum before the collision is going to equal to the momentum after the collision. Okay? Impulse is important. Impulse is force times time. Impulse is the same thing as momentum change. Momentum change is the mass time velocity change. We talk about collision time. If you can increase collision time, you can reduce the force of collision. And we gave practical scenarios where we use this concept. Airbags, rock climbing with nylon ropes. If you're falling off, if you fell off a roof, and you can bend your knees when you strike the ground, by increasing the collision time, you can reduce the force. So we in our next session we will do more practical situations. We will look more on actual collisions and work out velocity change, because that's one of the things that the law of conservation of momentum allows us to do. We can determine post collision velocities. So we're gonna stop at this point, and